Check your understanding 7.3 from page 335. Find the work done by the same force in example 7 over a cubic path. Y equals 0.25 m raised to the power of 2 x cubed between the same points A equals 0 and 0 and B equals 2m and 2m. These are our given. So we're going to find the work done. So the solution, express y and dy in terms of x and dx. Y equals 0.25 m raised to the power of negative 2 x cubed. Dy equals 3 times 0.25 m raised to the power of negative 2 x squared dx. So the infinitesimal element of work is dw equals f of x dx plus f of y dy. Substitute, and then we arrive this answer, final answer here. The work done is equals 35 joules. Understanding 7.4 from page 337. The problem is the spring in example 7.5 is compressed 6 cm from its equilibrium length. Letter A, does the spring force do positive or negative work? And B, what is the magnitude? So this is the drawing, and the answer of letter A, the spring force is the opposite direction to a comparison, as it is for an extension, so the work it does is negative. Letter B, the work done depends on the square of the displacement, which is the same for x equals plus minus 6 centimeters. So the magnitude is 0.54 joules. Check your understanding 7.6 from page 340. You are rowing a boat parallel to the banks of river, and your kinetic energy relative to the banks is less than your kinetic energy relative to the water. Are you rowing with or against the current? The kinetic energy relative to the bank is less than kinetic energy relative to the water. So the velocity of boat relative to the bank is less than velocity of the boat relative to the water. This is the drawing. The velocity of the boat relative to the bank is less than velocity of the boat relative to the water. Velocity of the boat relative to the bank is equals velocity of the boat relative to the water plus velocity of the water relatively to the bank. So the velocity of the boat relative to the bank is less than velocity of the boat relative to water. It is happen only when you are bowing boat against the current. Example 7.9, page 343 to 344. Lope the lope. The frictionless track for a toy car includes a lope. The lope of radius r. How high measured from the bottom of the lope must the car be placed to start from rest on the approaching section of track and go all the way around the lope? So this is the figure 7.12. The strategy sa free body diagram, the final position makita sa figure 7.12 mo na siya. Ang gravitational work is the only work done over the displacement that is not equal to 0. Dili siya 0. Since ang weight points the same of direction as the net vertical displacement, ang total work done by the gravitational force kay positive. Gikan sa work energy theorem, ang starting height nag-determine sa speed of the car adto sa top sa lope. Gikan diri padung ane. So Mano siya ang formula. Then where ang notation is makita sa figure, at the top of the loop, the normal force and gravity are both down. Naka-down sila. And the acceleration is centripetal. So, man siya ang formula. Second formula. So, the condition for maintaining contact with the track is that naay ma-involve na some normal force. However, ang n is greater than 0. Substituting for velocity to squared and n, we can find the condition for y sub 1. So this is the final solution. 7.7, page 344. Suppose the radius of the loop in example 7.9 is 15 cm and the toy car starts from rest at the height of 45 cm above the bottom. What is its speed at the top of the loop? So this is the free body diagram given, and then we apply the work energy theorem. This is the formula. Substitute, then divide both sides by m to cancel. B sub 2 squared, ato siya square root para mawala ang exponent, then the value of J, then substitute the value of gravity, the value of 2r, the value of y sub 1, and we arrive, the final answer is square root of 3 meter per second. This is the speed at the top of the loop.